lesson 53, describing a function's behavior. What we're going to do in this lesson is we're going to get a little more practice graphing things using just the scratch and sniff method for now. Making some graphs, and then I'm going to hang a whole bunch of vocab words on these graphs, and the vocab words are the main point of the lesson. So I only got 3 graphs here, so that'll be enough. You'll get enough words. So, okay, let's look at this thing. Square root of x minus 2 with the minus 3. Now, when you graphed a lot of things, what you want to notice here is, or what you get to notice here is that x equals 2 is going to be a sort of critical value. Now, I'm just putting that in quotes. There's nothing really critical about it. But it's sort of, in some sense, a critical value because that's where you'll have a 0 inside the square root. In fact, if you were to make an xy table, or let's be nice, an f of x table, anything that you plug in that's less than 2, like how about like a -2 or even a 0 or even a 1, etc., what you'll have is well, let's say I did plug in a -2. -2 minus 2 is going to be a -4 in there, and we're not going to make imaginary number, complex number graphs. We're just making real graphs for the rest of the term, real graphs. So it's not a real number. You can't plot the point, so I'm just going to put unreal. There's nothing there. There's nothing over there. Nothing. Nothing to graph. Nothing to see here, folks. But when you get to 2, finally, okay, so now you've got 2 minus 2 is 0. You can take the square root of 0. You get 0. What times itself is 0? 0 works. And then take away 3. Don't forget this part. So, okay, we can get started now. How about if we plug in x equals 3? 3 minus 2 will be a 1. Square root of 1 is 1. Minus 3 is this. Now, before I go plugging in 4, I don't want to plug in 4. Why don't I want to plug in 4? Because then I'll have to, 4 minus 2 is 2. I'll have to take the square root of 2. I'll have to get out my calculator. I don't want to get out my calculator. Phew. What you do is you say, well, you know, if this came out to 4, I'd be able to take the square root quite nicely. So how do I get that to come out to 4? I plug in a 6. Right? Be a little strategic with your xy tables. So I plug a 6 in, so that 6 minus 2 is 4. The square root of 4 is 2. 2 minus 3 is, well, -1. And what would be another nice number to plug in? Taking the square root of 4 was fun. Wouldn't it be nice to take the square root of 9? So if I put an 11 in there, 11 minus 2 will be 9. Square root of 9 is 3. 3 minus 3 is 0. And just because I'm having fun here. Let's see, how about a 16? It'd be cool to have a 16. Well, if I plug in an 18, 18 minus 2 is 16. Square root of 16 is 4. 4 minus 3 is 1. Okay. Now, unfortunately, this is way off our graph, but it was just too much fun. I couldn't resist. So, let's start making our graph here, folks. Maybe I'll clean up some of my messes over here. Okay, make our graph. We got some points. First of all, like I was saying, over here, -2, even 0, even at 1, there's nothing to graph. There's just nothing there. So what we're going to have to do is start at x equals 2, y equals -3, right about there. And since this is where the function starts, so to speak, usually we make a nice big dot to show, hey, that's where it all gets started. When x is 3, y is -2, so that'd be about here. I can make a smaller point now. When x is 6, y is -1. Okay. And so we're getting off the graph, but it starts here, and you can tell it's going to kind of, you got to go way out to 11 before you reach the x-axis. So it's just show an arrow to show that it just keeps climbing like that, right? And there, nice graph. Notice how nice I'm being, or how proper I'm being here, right? I have a big dot to show the end. That is the end. It does not continue. It does not do anything like this, right? It does not. So that's kind of nice. That's a nice thing. You want to think of when you draw a graph, you're communicating to people. So yes, I put the arrow over here to show that it does continue climbing. And then in particular, remember another thing I was saying when we were graphing stuff was always show asymptotes. And here's a nice example that I hope helps to explain why you should always show asymptotes. Because if you just took a quick look at this graph, right, if you just picked it up off the floor and looked at it, isn't the first question in your mind, hey, is there a horizontal asymptote here? Isn't that the first question you would ask? I mean, you see the thing going up like this, and it seems to be leveling out, and it's like, hey, is that a horizontal asymptote? Well, if you drew the horizontal asymptote, you'd say, yeah, there's a horizontal asymptote. And since you did not, or I did not, draw a horizontal asymptote, that means there is no horizontal asymptote. So you see how drawing it versus not drawing it, you're telling the person two different things. So if there is an asymptote, you make sure. If there's an asymptote, make sure you draw it. And if there isn't, make sure you don't, I guess. Okay, so now that we got the graph made, what do you say we get some vocab going? Vocab time. Vocabulary list. Now, unfortunately, it looks like I'm going to have to keep scrolling up and down as I do the vocabulary list. But one of the words for today is domain. And what is the domain? The domain is the set of all acceptable inputs. X's, right? You plug in, the X column represents your independent variable or what you're plugging in. You plug in values for X, right? I'm saying all the acceptable inputs because these are not acceptable inputs. The function spits them out. It says, oh, I can't do anything with it. You take that back. So the domain in this case would be, notice we can start, if you just look at the X column, we can start at X equals 2, and we can keep going forever, right? We can keep plugging in X's as big as we want. And so that represents the domain. And it's a continuous thing. It's like you can plug in not just 2, 3, and 6, but 2, 2.1, 2.05, 2.006, 2 point whatever. You can plug in all the values, all the real number values that exist between 2, including 2, that's why I say the less than or equal to, including 2, and going up to infinity. Now that's one kind of notation. There's another notation that a lot of people like because it's quicker to write. What do you think of that notation? That's called interval notation. I might as well write that down here. And I don't require you to use one notation or the other, just so long as what you're writing is unambiguous. I know exactly what you're saying. If I know exactly what you're saying, fine, we're fine. But that's called interval notation. So notice I use a square bracket because of the less than or equal to. It says that 2 is included in this interval. I use the round bracket because infinity is not included, and that's because infinity it's not a number, right? You can't say, hey, go to the number infinity. It's not a number. So we have to use a round bracket. It just means keep going without stopping. That's all infinity means. Infinity is more of a notion than it is a number. It's just, hey, keep going. Anyway, that's the domain, the set of all acceptable inputs. Ready for your next vocab term? Range. The range is the set of all possible outputs. So as you keep plugging in all of the acceptable inputs, X equals this. When you plug them all in, you end up getting, of course, a corresponding set of numbers over here in the so-called Y column, right? That would be the range, the set of all possible. So not just the -3, the -2, but all possible. So you look at the map and you can say, well, it looks like Y can take on any value from here, and because there's no asymptote, it keeps climbing forever. All of those values of Y are all possible outputs. So you would say, let's see, how low is that going? -3, which is included, all the way up to infinity. That would be your range. So it's almost like a domain, but you turn your head sideways and look at the y-axis instead of the x-axis, if that makes any sense. So anyway, in interval notation, what would you do? You would say, well, start at -3, include -3, square bracket, go all the way to infinity. You can't include infinity. It's not a number. You never get there. You never actually get there. Okay, now here's something to notice too. Always go left to right when you're writing these things. In other words, you would not, what are you doing now? I don't want to, don't go away. Where's the go away button? Go away, go away. Okay. What was I saying? Oh yeah, you would not write this. You would not write that. Nope, that's backwards. Because infinity is bigger than -3, right? You always want to put the small number on the left and the big number on the right. Make sure you do that, or it's not really proper interval notation there. Okay, so we've got our domain, we've got our range. That's 2 words. There's more words. Ready for this one? There's something called, well, notice right here, the function comes down and it doesn't go any lower than that, right? We call this point a minimum. Seems like an okay word, doesn't it? Okay, that is, in fact, it is the lowest minimum possible. There's nothing lower than that, right? So we call it an absolute, or another word you'll hear is global minimum. It's the lowest the function goes, the lowest output you ever get ever. That's the absolute global minimum. And we say the minimum is, and you talk about what is the minimum output. The minimum output is -3. The minimum is -3, and it occurs at, in other words, when you set your dial to x equals 2. Okay, so always you put the y there and you put the x there. So you have an absolute or a global minimum of -3, because that's the minimum, that's the output. Output is, we're interested in the minimum output. The minimum output's -3, and it occurs when you set the dial to 2 at x equals 2. Okay, so just keep the of at kind of straight, please. So an absolute global minimum, yeah, that's cool, right? By the way, you'd say, well, where's the maximum? What's the maximum output? And if there were an asymptote here, I suppose you'd say something like it's never going to go above 0 or whatever wherever the asymptote is. But it increases forever. And because it increases forever, please don't say the maximum is infinity. Say this, say no maximum. There is no maximum. It keeps climbing forever, okay? And again, infinity is not a number you can reach. So the maximum, well, there isn't one. It just keeps climbing. It climbs indefinitely. Never, ever stops, ever, 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 ever stops. One more word for this one, for this little graph here. So, okay, where our domain starts here at x equals 2, and notice the function is climbing. There's another word you can use to describe the function. Actually, we don't use the word climbing. We say it's increasing. The function is, the function is increasing over the interval, because increasing happens, you can't say, hey, right there I'm increasing. No, you're not right there, you're just stuck there. At that point you're just stuck there. You're not increasing when you're just sitting there, standing there. You increase as you walk. So as you walk across this interval, the function is increasing. Get it? It's increasing because it's going up. As you go to the right, it's going up. So increasing over the interval, and by the way, what is that interval? It starts at 2 and it goes up to infinity. So you would write this. Well, I suppose you could write it. Suppose you could write it x greater than 2, or if you want, you could write it 2 to infinity. Notice I am using round parentheses here. And it goes to what I was just saying about you can't be increasing while you're sitting at a point. So you wouldn't say you're increasing at 2. You're not doing anything at 2. And besides, if you look to your left, what are you doing? You don't know what you're doing, right? So increasing is kind of a two-sided idea. It's like I'm increasing because over here I was lower, over here I'm higher, so I'm increasing. Get it? It's like you have to look both ways to decide whether you're increasing or decreasing. So please keep this in mind. You use round, that's supposed to say round. You use round brackets when you're talking about whether you're increasing over an interval or decreasing is the other possibility, right? So there, we get some good words there, don't we? So going nice and slow and careful, because that's what you should do. You should go nice and slow and careful and make sure you agree with every single thing you're saying, and you never have a question about anything that you don't first, go look it up and make sure you're getting it right before you say that's my answer. Okay, let's do another one. Let's switch back to blue. This orange color's freaking me out. Okay, sketch a nice graph of that thing. Okay. We've been using the so-called shotgun approach to make our graphs. This is a g function, I guess. Where would you center your shotgun? Well, you look at inside these absolute values and say, well, x equals -2 is going to be interesting because that's where this equals 0. And if you plug in something a little bigger, it's going to be a positive. If you plug in something a little smaller, it's going to be a negative. So I'm going to center my shotgun at -2. So maybe I'll put that here. And let's go back a couple places. I don't know, -3, -4. And then let's go forward a couple places, like -1, 0. Maybe go to the other side of the y-axis while we're at it. Okay, now let's start evaluating. If I were to plug in a -4 right there and add 2, I'd have a -2. But then I'd take the absolute value and I'd get 2. And 3 minus 2 is 1. Cool. If I were to plug in a -3, I'd have -3 plus 2 is a -1. But then I'd take the absolute value and get 1. And 3 minus 1 is 2. Cool. Now let's plug in that -2 we were talking about. See what I mean right here? -2 plus 2 is 0. 3 minus 0 is 3. Now we keep going. We get to -1. That's a -1. -1 plus 2 is 1. And the absolute value of 1 is 1. And 3 minus 2 is 2. See, now we're doing this again. We're going back to there. We've got a y equals 2 again. Let's plug in 0. Well, 0 plus 2 is 2. Absolute value of 2 is 2. 3 minus 2 is 1. Cool. And then we plug into 1 just for fun. 1 plus a 2. 1 plus a 2 is a 3. 3 minus 3 is a 0. Is a 0. Is a 0. Okay, we can start plotting some points here. So when x is -4, I go down to -1. Cool. When x is -3, why did I say -1? What's wrong with my brain today? When x is -4, y is 1. Let's do it right. What do you say? When x is -3, y is 2. Yep. This looks better. When x is -2, y is 3. Okay, cool. When x is -1, we're back down to 2. When x is 0, we're back down to 1. When x is 1, we're at 0. And I think you can see what's going to happen here. These look pretty straight, right? It's going to be one of those upside down V shapes. If you want to prove it yourself, you can plug in 2. 2 plus 2 is 4. The absolute value is 4 is 4. 3 minus 4 is a -1. So yep. And over here, I'll bet your socks it's going to go like this. I'll bet your socks, not mine. Just kidding. Okay, so anyway, it's doing this. Whenever you see x inside of an absolute value, you're kind of expecting some kind of a sharp V shape. And so there's our sharp V shape. It happens to be upside down. It happens to be kind of moved over a little bit. But there it is. There's our graph. Nifty difty. Ready for some vocab? Maybe I'll keep the vocab in blue time this time. Vocab list. This vocab list will be about the same size, I think. First of all, same word. What is the domain of f? Can you tell me? Again, the domain is the set of all acceptable inputs. Acceptable inputs. What am I allowed to plug in here where, I'll actually get a number back out? I'm allowed to plug in basically anything I want, right? There's nothing that's going to go wrong here. There's no square root of a negative. There's no division by 0. Nothing's going to go wrong. All real numbers. All real numbers. Which, if you want to use interval notation, you'd say everything from -infinity to +infinity. Again, round brackets, please, on your infinity. You can't reach infinity. You can't start at infinity, because infinity, you never get there. So anyway, the domain is all real numbers. Okay, cool. Ask yourself, what's the range? Well, it's not all real numbers, because coming along the, you would look at the y-axis and you would say, wow, I've got y values here and here and here. I've got y values here, here, and here. And of course it goes down forever, so I got y values all the way down to here. But there's no y values up here. There's nothing up there. Oops, there's nothing up there. So y is limited, right? Now you always make your interval starting at the small side. What are you doing to me? Okay, starting at the small side. In other words, y is coming, we're going towards -infinity. Well, that's small. And we can come as high as y equals 3, it looks like. So if you want to write it that way, you can write it that way. If you want, you can use the interval notation, which tends to be quicker, I guess. So notice the square bracket on 3 to show that we do include 3. Again, small to large, -infinity to 3. Okay. Make sure you put it in that order or it's not actually correct. So, how do I get rid of all this stuff? Ooh, that was quick. All right, what other words we got for you today? Well, let's talk about, remember the other function had this minimum. Well, this one has not a minimum, but it's got a peak. It's got a highest possible value right there. Guess what we call that? We call that the absolute. Absolute meaning there's nowhere else that goes higher. Sometimes global is the word we use. You can pick whichever one you like. Absolute or global maximum. Now try to remember the of-at stuff. The coordinates of this point, of course, are x is -2, y is 3. That's the coordinates of the point. So what is the maximum value? The maximum value means the maximum output. The maximum value is 3. And it occurs when you set the input, or at, in other words, -2. Okay, make sure you state those numbers in the right spot. Of 3 at -2. Okay, the maximum is referring to the output or the input, and where we say, well, where is it? It's at x equals -2. That's where it is. Okay, so again, it's just you want to pick up the lingo. What else we got? Notice we don't have any minimum this time. It goes down forever, so I guess we could just say no minimum. Remember that increasing thing? This one goes up and it goes down. So we could say it's increasing over the interval, and we'll state it in a second. There's also a spot where it's, or an area or a range where it's decreasing over, or there's an interval, if I want to speak correctly. There's an interval over which it's decreasing. So it's increasing where and it's decreasing where. Well, increasing, decreasing is a left to right thing. You read a book left to right, right? So as you were, don't look at this arrow, in other words. It looks like the arrow is pointing down, but that's not what matters. What matters is that as you keep increasing in x, as you keep reading to the right, it's going up. Okay, so that's where it's increasing. It's increasing starting way out at -infinity until you get to here, until you get to x equals -2. So, -infinity to -2. And again, you always use round parentheses when you're talking about intervals of increase, decrease. Because as I was saying before, when you're sitting at a certain point, you're not increasing or decreasing, you're sitting there. The notion of increasing and decreasing involves looking on both sides. And over here, you're not, you're going the other way all of a sudden, right? So you would not say you were increasing at -2. In fact, you're not doing it, you're sitting, you're at the peak, you're the maximum, right? So no, you're increasing there, and because as you read to the right, here you're going down. Okay, so there's where it's decreasing. It's decreasing over the interval, start at -2, go to +infinity. Okay, so I think we got those words taken care of. Cool. Got some more funky words for you on the next page. Let's get rid of that. Okay, so we'll end with a kind of a zany one. Hey, you like that one? Look at that function, huh? The mother of all functions. No. That one requires a fresh sip. Okay, so what are we going to do? First of all, what we have here is, it looks like we got two pieces. So if x is between -3 and 2, you're supposed to go here and figure out your y values. And if x is something bigger than 2, or equal to 2, you're supposed to go here to figure out your y values. Well, this part's going to be easy to graph, this part here. It says if x is greater than 2 or equal to 2, y is 5. So here's x2, come up to 5. If x is anything bigger than that, stay at 5. Okay, so that's what's happening there. Put a nice big dot there to show that that's a starting point. It doesn't continue to the left right there. At least not along that line anyway. Okay, so that part wasn't so hard to graph, that bottom part. Now it's the top part we got to figure out here. We'll do this by shotgun approach. Now notice that you should only use values between -3 and 2 because we're restricted here. It's called a restricted domain. So let's see now here. X cubed minus 4x. The way I like to graph these polynomial type things is I like to factor them. So pull the x out and you're left with an x squared minus a 4. And remember, that's a difference of 2 squares. So if I factor it out completely, I like to work with that form. Because, for one thing, it's easier to find intercepts. I suppose it ain't so hard to find the y-intercept. Come on, you. So where's the y-intercept? What you would do is you would make x equals 0. What you would do is you would plug in 0 into your function. And I suppose it doesn't matter if you plug in here or here. If you plug in 0 into either one of those, you're going to get 0. So the y-intercept is 0. Okay, cool. I'm going to plot that point right now. What about the x-intercept? What you do is you set the function equal to 0. Technically, I should have used an h, not an f there, right? So anyway, you would set the function equal to 0. Not set x equal to 0. That's how you get the y-intercept. Set the whole function equal to 0, which is kind of like saying set y equal to 0. And that's why I really like this factored form here, because it's easy to see where this function equals 0. We have x-intercepts at, well, if x is 0, that makes the whole thing 0. If x is 2, it makes the whole thing 0. If x is negative 2, it makes the whole thing 0. So when you have factored form, it's a lot easier to find your intercepts. And knowing your intercepts is like huge, right? It really helps you get your graph going. So x-intercepts at 0, okay, we got that point plotted already. At 2, now you want to be careful here. I don't want to put a dot there. Why not? Because it says right there x is less than 2, not equal to 2. So I don't put a solid dot there. I put an open circle there because we do get awfully close to it, but we don't reach it. I mean, this equation. We take this equation, we take the output of this equation as we get it very, very close to 2, but we don't actually include the point at 2. So it's an open circle there. Also at negative 2. So we have an x-intercept over here. Okay, cool. So again, make sure you get that open circle going. Man, this thing is picky. Okay. Bunk, 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 bunka. All right. Now we should probably start doing our scratch and sniff to get some more points here. And looking up here, again, since the domain starts at negative 3, there's no reason to plug in anything less than negative 3. So I might as well start at negative 3, right? So let me just start at negative 3. And I suppose you could plug into either one of these forms, of course. I like to plug into the bottom form because x is negative 3, and then you get negative 3 minus 2 is a negative 5, and then you get negative 3 plus 2 is a negative 1. And so what does that equal? That equals a negative 15. Wow. Well, that's way down there. So when x is negative 3, I go, I'm just going to kind of do this. I'm going to label the point, and then it's, you know, the graph is not quite, whoops, the graph is not, come on, it won't let me hit that. Okay, so the graph is not quite to scale. In fact, if you were let me try to draw that a little more neatly. Come on, stupid phone. You could draw lines like this to show that it's kind of going like this and that this is a break in the scale. So negative 3, negative 15 is the lowest point that we go here. When we're at negative 2, of course, we're at 0. How about when we're at negative 1? When x is at negative 1, now what's happening? Well, again, I like to plug into my bottom form here, my factored form. So x is negative 1. Negative 1 minus 2 is a negative 3. Negative 1 plus 2 is a 1. That's giving me y equals 3. Okay. So it goes up to there. Cool. I wonder if that's as high as it goes. You might want to plug in some in-between values and see what's going on in between there. So if I plugged in negative 1.5, and if you trust me, I just got out my calculator and did it. When x is negative 1.5, I got 2.625. And I also plugged in negative 0.5, and I ended up getting 1.875. In other words, the 3 does seem to be about where it is. So if I can plot these points, negative 2.625 here, that would be something like that. And then 1.875, so it seems to be dropping a little faster over here. So it's doing something like this. Whoa. Try to make it look smooth. Okay. What happens when we go over here to x equals 1? In my factored form, I'd have a 1 times a 1 minus 2 is a negative 1 times a 1 plus 2 is a 3. So that's a negative 3. Well, how do you like that? Kind of a symmetry of sorts there, huh? And I think I'm just gonna believe that it does this. You can verify if you want, but I'm pretty sure. I've graphed so many things. You often get these little symmetrical wiggies around the origin, so I'm just going to assume that's what it does. Okay, cool. There, we made our graph. Kind of a funky graph, huh? So it starts way over here at x equals negative 3, y equals negative 15. It kind of climbs really fast, gets up to here, turns around, comes down through the origin, comes down to here, turns around, comes up to here, kind of stops, and then jumps way up to here. I guess you can't really see what I'm doing here. So turns around, comes down, jumps up to, and then jumps way up to here and stays at x equals 5. Funky behavior, man. Funky. We're talking funky. Okay, so we need our vocab. What color is the vocab going to be in? Vocab's good. Let's do green. I'm liking the green today. Okay, vocab time. First thing I'm going to say is we got a name for this weird thing here. This function that was kind of defined in 2 pieces. What we call that is h of x is called because what we call that is piecewise defined function. That's an E. Piecewise defined function. So that happens. Sometimes functions are defined in more than one piece. It's a piecewise defined function, and here's another good word for you. You see this thing right here where it goes from here up to here all of a sudden? Like it's there and then it's there, kind of like a quantum particle or something, or kind of like a parking lot. You're there for 1 extra second and the price goes up by $20, you know? Okay. So anyway, so that's called a jump discontinuity. And you say the jump discontinuity is occurring at, well, it's when you set your dial to 2. And I'm being a little redundant to say x equals 2, but if you just say at 2, it should be good enough, but sometimes I like to be a little redundant and careful. So at x equals 2, we have just a jump discontinuity. Okay, cool. What about these other vocab words? Can you tell me what the domain is? Can you tell me what the range is? Can you tell me where it's increasing over the interval? Can you tell me where it's decreasing over the interval? Let's just look at those 4 first. The domain is the set of all acceptable inputs, and probably the best place to look at the domain is right here. So it looks like you're allowed to start at x equals negative 3, and you're allowed to use, you almost say, oh, can't use 2, except you can use 2 right here. Go to infinity and beyond. So the domain would be everything, including negative 3, up to infinity, which by definition you cannot include. That's the domain. Range. What do we got for a range here? Well, the range is going to be kind of funky. Now the range, you have to look at the graph. So I'm looking at the graph, and I'm saying, okay, you're looking at all the y values, the outputs. And you'll notice right away, you never go any lower than negative 15. The y values come up. They go as high as 3 here. Now, these y values are all just, we don't need to include those separately because they're all, if I say everything from negative 15 to negative 3, that includes all of these. But then you get this one other y value up here that you have to include. So you've got kind of like 2 parts to your range. You don't use any of the y values in between because there's no points that have y coordinates of 4, for example. So for the range, you'd have to say, well, y can start at negative 15, square bracket, negative 15. It can climb up to 3, it looks like. including 3. So you end that interval. And then you got to add this one value 5. How do you add one value? Well, one value isn't, go away. One value isn't really a interval, but it is a value. So you just use your standard curly brackets. And then to say that both of these pieces belong in the range, we usually use a union symbol. So it just says join those together. So the range includes all values between -15 and 3, including -15 and 3. And would you stop? Go away. How did I get this here? Okay. And the value 5. Okay, cool. Domain range. Okay, increasing. Where is it increasing? Well, if I were to erase this green stuff for now. Increasing means that as you read, going in this direction, where is it climbing? And it's climbing from here all the way up to here. And then it's climbing again from here to here. Those are where it climbs. So we've got 2 answers to this one. It seems to be climbing, and then you give the x values. It's climbing over to, let's see, this is starting at -3 and going to -1 for x equals -3 to -1. And you always use round brackets for these, right? I suppose I can fit that here. Always use round brackets for ranges of increasing, decreasing. And then, except I have to list the other interval, don't I? Because it's also increasing from here to here when x is 1 to x equals 2. So there's actually 2 intervals where it's increasing. Now I'm not going to join those with the union symbol because, again, because it's like 2 answers. It's like 2 separate answers. The range is supposed to be a single object. The increasing over the interval is you can give multiple answers to that. Decreasing. Where is it decreasing? Well, you can kind of tell it's decreasing here. So from x equals -1 up to x equals 1 is where it's decreasing. And then I got another word for you. It's constant over the interval. So in case you were wondering, what's this doing? It's not increasing, it's not decreasing. Nope, it's staying constant. You've got a constant output. Get it? The output remains the same. It's a constant output. So it's constant starting at x equals 2 and just going forever to the right. Okay, so constant over the interval, x equals 2, going all the way to infinity. So we got that extra word, increasing, decreasing, constant. Okay. What about the maxima minima type stuff? Well, we have a global, or what you might call an absolute minimum. Might as well start at the low part. Remember, that's as low as it goes. Don't go any lower than that. That would be your absolutely lowest output. Your global, looking at the whole function, output is smallest at, well, it's -15 is the smallest output, and it occurs at x equals -3. I suppose if I want to be redundant, I'll put it this way, at x equals -3. Might as well, it's probably more clear. Okay, that would be the, and then, but notice this thing. What's that? That's a minimum. It's not the lowest part on the whole function, but it's a minimum. If you were sitting over here, it would feel like a minimum, right? It would feel like you were bottoming out. We call that a local or a relative minimum. And what's the minimum there? The minimum is, again, you're talking about minimum output. Looks like it's -3, and it occurs at x equals 1. -3 at x equals 1. Okay. So we've got the absolute minimum right there. We've got this local minimum right here. Here's well, you wouldn't call this the global maximum because we got higher output over here. But it is a local or a relative maximum. So let's put that one next. A local or a relative maximum of, and remember the coordinates of that point were 1, 3. So the output is 3, and it's occurring at x equals 1. Whoa. That's at -1, isn't it? So that yeah, that's a -1. I kind of messed that up. -1. That's better. Okay, and let's see. And then we can talk about a global, of course. And the highest this function ever goes is 5. So I do want to say that. I want to say the maximum output is 5. So I'm going to say it's 5. But at, it's hard to say at, because it's at all of these values of x. So I guess I'd say at, maybe I won't say at, maybe I'll say, come on you, I'll say along x being from 2 to infinity, something like that. Yeah, because that's telling me that's where the maximum output is. It's in a lot of places. Everything from 2 to infinity, that's where you meet your absolute max. So I got the increasing, decreasing constant. I got basically 4 kinds of extrema, we call these. Absolute max, local max, absolute min, local min. So that's 1, 2, 3, 4, 5, 6, 7 for the increasing, decreasing constant. 8, 9 for the domain range. Yeah, and then if you use piecewise defined function and jump discontinuity, that's up to 11. We're up to 11 vocab terms. That should be good, right? 11 vocab terms. And with this vocabulary, you can describe how a function behaves, and even better, if someone uses the words, you'll know exactly what they mean. Is that it? I think that is it. So I hope you have a little fun with this one.